Welcome everybody. We will wait for about a minute so that everyone can join. So welcome everybody. I will start now, and hopefully everybody has joined, or if people join during my introduction, it's okay. So it is my pleasure to introduce, my name is Chrysula Tsoga, and it is my pleasure to introduce our speaker today, Professor Maarten V. Maarten earned his PhD degree in technical science from Delft University of Technology. And he then spent 10 years on the faculty of the Center for Wave Phenomena in the Department of Mathematical and Computer Science at the Colorado School of Mines, followed by 10 years as a professor in the Department of Mathematics and the Department of Earth and Atmospheric Science at Purdue University. While at Purdue, Maarten was the director of the Center for Computational and Applied Mathematics, and he also founded the Geomathematical Imaging Group in 2007. He joined Rice University in 2015, where he holds the Simons Chair in Computational and Applied Mathematics and Earth Science. He is also a visiting professor at the Department of Earth, Atmospheric and Planetary Science at MIT, and at the Graduate University of the Chinese Academy of Science in Beijing. Among several awards that Professor De Hoop has received, let me mention that he won the 1996 J. Clarence Karcher Award from the Society of Exploration Geophysicists, and that he was elected a Fellow of the Institute of Physics in 2001. His research interests are in inverse problems, deep learning, microlocal analysis, and massively parallel computing, with applications in earth and planetary science. He has published 170 papers, including in Science and Nature Communications, and today he will talk about his recent work on deep learning in wave-based imaging and inverse problems. I really look forward to the presentation of Maarten. I should mention that Maarten does not have a very reliable internet connection where he's right now, and therefore he has pre-recorded his presentation, and he sent us the video which we will play. So before giving the pass to Maarten, if he wants to say hello, I want to mention to all the participants that if you have questions during the talk, please click Q&A in your webinar controls and type them there. You will also notice a chat function which you can use, and hopefully the connection will be okay, and then Maarten will be able to address them at the end of the talk. Thank you all.
Thank you, Chrysula, for the kind introduction, and I would like to thank the organizers for the opportunity to give this presentation. As Chrysula said, I'm working at the moment in Costa Rica, remote, with very limited internet connections, and hence it has been pre-recorded. It's a great pleasure to be here, great pleasure to connect to everybody through Zoom, and at this moment I will let the pre-recorded presentation take over. I would like to begin to thank the organizers for the opportunity to give this presentation. And I'm sure many of you are very pleased that the Science Imaging Science meeting could proceed in virtual format. This is a talk about connections between deep learning, wave-based imaging, and deep learning and wave-based inverse problems. The results are from a couple of papers, joint work with Ivan Dokmanic, Conor Kotari, Matilassas, and Christopher Wong. The wave-based inverse problems, two that I will discuss. One is, in some sense, a linearized version that leads to imaging. Examples are the thermoacoustic, medical radar, seismic imaging. And in linearized imaging, typically we assume a separation of scales and, for example, would like to image features in the small scales, such as a source, reflectors, and the like. The wave-based inverse problem, the fully nonlinear inverse boundary value problem for the wave equation that I will touch upon. I'll touch upon an approach and techniques that goes back and make use of boundary or scattering control, and then followed by reconstruction to recover the wave speed. The aim of this talk is to discuss neural networks and their properties, the architectures of which are modified and modified in accordance to the analysis of an imaging and an inverse boundary value problem for the wave equation. In some sense, this talk is a tale of two deep neural network architectures, two very basic ones, the UNet that will relate to the imaging, and a recurrent neural network that will relate to the inverse boundary value problem for the wave equation. The focus will be on approximation. Can we approximate the imaging and the reconstruction using boundary control in a particularly good way by deep neural networks? But the interesting questions are these of generalization. So suppose we have a set of training data. How well from these training data does the trained network generalize? And perhaps most importantly, what about the inductive bias, making use of analysis-based architectures? Can we get our hands on inductive bias, i.e., could the networks perform in particularly well outside the training data? And of course, implicitly, we are interested in the reconstruction or estimation. So let me start with wave-based imaging, learned wave-based imaging, where we go back to the UNet, and I will very roughly introduce what we have coined as the FIO-net. In wave-based imaging, I'm going to assume a separation of scales. There's a smooth background wave speed, and there are singularities occurring in this background wave speed. It could be sources, or it could be reflectors. So what we do is we decompose, say, the wave field into wave packets, and these wave packets propagate along rays in the background. And what we see here on the left is an example where we put in, say, 3 sources, S1, S2, S3. They generate waves. We decompose it into a wave packet. The wave packet will propagate in either direction towards the recording surface, and say we record it at position A after traveling over time t2. But of course, this wave packet also travels into the interior of this domain, the opposite direction as well. And so the recordings of these 3 sources are visible over here, where we have sensor traces along the recording surface, and that measure the incoming signal as a function of time, indicated over here. And then the goal would be to invert or to infer from these arrivals the sources characteristics. As a second problem, we look at the reflection problem. We have a source, generates a wave, decompose it into many wave packets, they get reflected at interfaces, and then refracted and reflected, and the reflections we measure in the recording surface. Now, all of these again depend through a separation of scales on a background wave speed map, and let us indicate that map by sigma. So these wave-based imaging problems can quite generally be described by Fourier-Nicolai operators. I'm going to skip the details, but give the very basics. So let us take U, being, say, a wave field, and let's Fourier transform U. Xi is the dual to X. then the action of a Fourier integral operator acting on U is given as follows. You have the Fourier transform of U, and then I subject it to an integral operator with an oscillatory kernel that has a phase S, parameterized by sigma, the background wave speed, and an amplitude A that depend on the output point and the dual psi. The separation of scales in terms of identifying a coarse background wave speed, that can be further represented or sparsified via encoder techniques that I will not go into. Now, these Fourier integral operators have been studied from many points of view, also computationally, using wave packet decompositions or curvelets, and many papers, but I would like to particularly mention the work of Smith in the late 90s, with the work by Candace and de Manet a bit later, and more recent work from our group to give explicit discretization strategies using a particular decomposition that I will highlight now. And that decomposition is the dyadic parabolic decomposition of phase space. Here I show the Fourier plane, the psi plane. We decompose this Fourier plane in NLI dyadically with 2 in the power k, length 2 in the power k, radial length 2 in the power k, and width 2 in the power k over 2, form boxes B nu k that identified by direction and a scale. And the tiling is initiated via a partition of unity, chi squared, which essentially can be thought of as filters. And here I show the support of chi hat of these type of filters that initiate the tiling of this space. And why do we do that? Why does one do that? Well, that allows us to expand the phase in the oscillatory integral, the kernel of the Fourier integral operator, in the Taylor series on a box, in particular in the thin direction of the box. And here we see the first order term, and I write here a second order term, and of course there are higher order terms. Let's first look what this first order term does. What we do is we introduce U hat nu k, which is what I would call now the box B nu k, box filtered version of U, in Fourier written as a Fourier multiplier. And then we can invoke this Taylor expansion and calculate what this Fourier integral operator does. Let's just do that to the leading order. And what we get is U nu k with its argument, the gradient of S with respect to psi, which can be viewed as some sort of diffeomorphism that depends on the direction. So in some sense, U nu k has been sort of moved around and deformed a little bit. Indeed, for each nu, we have a diffeomorphism T, striped over here, that is dependent on the direction U and the output location Y, that captures the geometry induced by the core scale wave speed. But now let's go further in the expansion, get a better approximation. And this is well known how these things are done. I give here a quick sketch. Here I have the amplitude and the phase, the second order term of the oscillatory integral that generates the Fourier integral operator, indicator function on a particular box. That can be subjected to a low-rank separated expansion or representation where R is essentially proportional to the log of k, and the separated functions are functions of y and functions of psi. These are Fourier multipliers, filters, and these are just multipliers. So substituting that in the action of the Fourier integral operator on the function u, what happens is we take the Fourier transform of u, we apply the partition of unity. Well, these can be thought of as filters. We think of the new case now as channels, then reminiscent of the theta, we get here thetas. These are, again, filters. But since, in general, the boxes need to overlap to form a partition of unity, we allow here not just filters in UK, but we allow that there's also some interaction between UK and U prime K prime. Then we get the first order term of the Taylor expansion, the diffeomorphism that is applied after this filtering. And then we apply the multiplications, add the terms, put it in parallel, and then of course in the end, combine them, add together the contributions from the different boxes. And indeed, this gets already the appearance of a network. The details I will leave out in this talk. That is, we start with U and we apply these filters, these box filters, using the dyadic parabolic decomposition. We think of these as fixed filters, layers in a network. Then what we do, we apply the theta filters that we can learn, and these filters act also between channels, let's call that H. And after that, we apply multipliers, alpha, and of course we combine. So how very roughly the network would look like is we have the convolutional layers to tile the phase space. We apply this low-rank separated representation, and in fact, mathematically, this can be well represented rigorously via a U-net, some form of a U-net, after which we apply the diffeomorphisms. We do that delicately with a bilinear interpolation, a standard technique. With neural networks, and then we apply the multiplications and do all the combinations. Now we can numerically estimate that very precisely, and that is done in the early work with Duchkov and Anderson. So here we have essentially a very particular neural network that is not a U-net, but has very delicate modifications. We sort of encode that we work with wave packets in some way, and we encode the geometry of wave propagation, scattering, and imaging by explicitly putting in these diffeomorphisms. And so let me immediately jump into how this performs by showing you a few experiments. I'll choose 2 experiments out of 3 that we have done. The first one is, let us take sources in interior, and for training, we take little boxes with edges and corners as sources that go off, and at a later time, you measure the wave field, like over here, and then the goal is from this wave field to recover the sources, which is just a matter of time reversal. Indeed, time reversal will be a common thread through this entire presentation. And here on the right, I put a source at the top of the recording surface. I emanate waves, wave packets that get reflected from reflectors. These are examples of what we will use in training this particular network of line segments. And we measure the reflected signal from this single source at receivers right at the top of this domain. And we would like to recover the reflectors from these data. The background here is described by lenses. In fact, we use Gaussian lenses. So we have the formation of caustics, and hence here you can see the complexity of this wave field. So let's do the first problem, the reverse time continuation problem, and find the sources. So how this network performs, how do we train it to say, is we actually use optimal transport, a particular implementation of the realization of optimal transport to do the training. I'll show here first how the network performs if we do in-training, if we restrict ourselves to an in-training distribution, i.e. The little boxes with edges and corners. So here are examples of data where we show how the network performs, testing. And here we show the standard U-net, which is a powerful network to do tasks like this. And indeed, it performs well for in-training distribution. The FIO-net essentially performs equally well, modulo a few differences. By the way, here's the ground truth at the bottom. But the interesting part is if we go out of training. And so if we take random shapes, the U-net, say a baseline network that would approximate these operators sort of generically, is not doing very well. The FIO-net seems to really have learned the wave-based imaging, seeing triangles and circles and the like. This is the ground truth. Same story for MNIST, if we take the numbers 2 and 3. The U-net is trying sort of to find the numbers by looking at boxes that fit the numbers, but does find the numbers, and this is what the FIO-net does. For reflectors, exploding reflectors, the difference in performance is truly significant. Here we see some artifacts for the Evayonet, but they are real because we only used one source to illuminate. We used only, sorry, not one source, we used only the receivers over this finite domain to illuminate these reflectors. And here on the right, we use the edges of celebratory phases, the celeb A example, the benchmark data. And what you see over here, again, that the UNet, the standard network, does not perform well, whether the Evayonet, here's the ground truth, does what it's supposed to do. And so this is a nice indication to see what the inductive bias is of the Evayonet versus the UNet. So let us illustrate that very briefly. We illustrate that within training by increasing the number of training samples in the training distributions from 1,000 to 3,000 to 30,000. And on the left, we show every time the UNet results, and on the right, the Evayonet results. The Evayonet really starts to perform already quite well with relatively few training data, but eventually the UNet catches up to a degree that is true for the random shapes, though not perfect by any means. But then for MNIST, and certainly the reflectors and the faces, the face edges, the UNet barely catches up in any way by adding training data. So the Evayonet seems to truly have learned the wave-based imaging principles. Show quickly another example of reflector imaging. Again, in training distribution on the left, here is the ground truth. Here, you need to account for illumination because we have only a single source. So we should really compare the results with respect to the illuminated ground truth. The Evayonet and the baseline UNet results are essentially comparable and do the job. Then we go to smooth reflectors. And the UNet doesn't really succeed in continuously connecting the pieces to form the reflectors, and the Evayonet does. We shuffle the reflectors by adding faults, and the faults do show up over here in the Evayonet, the UNet not, and then here we take random reflectors and the conclusion is the same. So this gives an idea that doing modifications in a network based on understanding mathematically the imaging problem, this modification network provides you very favorable out of training results and gives a real handle on inductive bias, as it seems. Let me now go to boundary control, the inverse boundary value problem for the wave equation, and go deeper in the question between neural networks and inverse problems, and study learned direct nonlinear reconstruction. Boundary control, I show here a very simple picture. Roughly speaking, tries to do the following. Here I have a domain, a two-dimensional domain. I want to put in a source distribution as a function of time at the surface that indicate here, this is time. And I would like to view the source distribution as a control to prescribe a function in the interior. Here we try to find an indicator function in the interior that is precisely bounded here by a piece of a circle and this line, interior domain. So we're trying to find a control that generates what we call a domain of influence that is one above this line segments and semicircle and zero outside. And boundary control probably gives you a way to do that, to find it without knowing the wave speed. So I mentioned some prior work. There is a vast literature. The boundary control method goes back to the work of Belyshev and Belyshev-Kurilev, early 90s. In the context of time reversal, iterated time reversal, that was analyzed by Bingham et al. In 2008, and we modified the boundary control method further to make it amenable to computations and algorithms in 2016. We'll make use of old ideas, ideas of unrolling and Neumann networks, that of course go back to Gregor and Lequin, ideas of Adler and Cooktam, and the Neumann networks introduced by Gilton, Onji, and Willett. We'll discuss approximation using work by Jarodsky, 2016. From the boundary control, we learn a notion of sparsity in a particular way of regularizing, in particular regularizing the loss function to train the network and analyze generalization. These ideas in all sort of contexts have been studied by quite a number of groups, and I list here the number of groups of work related to sparsity, Lipschitz bounds and the like during training approximation generalization, though not of the particular type that we consider here. And then generalization goes back to using Hoeffding's inequality and some techniques developed after that. So boundary control. I'm going to discuss the simplest possible case, namely the one in space dimension 1, though everything I say generalizes, but to keep the presentation as simple and transparent as possible. Here I have the wave equation, C is the wave speed. I apply a Neumann boundary source, H, as a function of time. The manifold with boundary is just a half interval, 0 to infinity, and I consider the problem from time t equals 0 to 2t with 0 Cauchy initial values. The solution I write as u of h, h indicating the particular boundary source, and that allows us to introduce the Neumann-to-Dirichlet map, lambda, that maps the boundary source to the solution at x equals 0 in the given time interval. I mentioned already the domain of influence, M of S, of a boundary source is controlled S by a maximum distance measured in travel time from the boundary. And so the boundary control problem is find the boundary source, H of S, that actually makes sure that if I solve the problem in the interior and look at the solution at time, say number t, that it gives me the indicator function on that domain of influence. And we want to do that without knowing C, which is indeed what the boundary control method allows us to do. Once we have that, it's a few operations to do to then recover actually the wave speed from having these boundary controls. So what we do is we introduce already some representation, sparse regularization that we can justify, make rigorous, by introducing some basis of dictionary, say psi. So B represents this type of decomposition of the boundary source H, and we write the components as bold H. So the boundary control can then be cast into some minimization problem indicated here. Try to find a control H such that U at time t matches the indicator function. And then we apply a regularizer, the sparsity regularizing L1 norm with a regularization parameter alpha. And so that's what we would like to find. The question is, does that indeed give us a valid way of finding the boundary control? I'll comment on that in a moment. For later use, I introduce a projector, PS, that in this one-dimensional case just amounts to multiplying with the indicator function on the time interval t minus s t. Now, the boundary control technique makes use of a key principle, an introduction of what is known as the connecting operator. Let me write W as the solution operator that maps the Neumann boundary source to the solution at time t. And let me introduce the adjoint, W star, and form the adjoint applied after the solution operator, and that is the connecting operator. With this connecting operator, we can rewrite the minimization problem in this form, finding the minimum of this form, where these are L2 inner products. Now, in time, they live essentially in the space of sources, of boundary sources, inner product as well, and here's the regularization term. And here is this connecting operator, K. The solution operator, the solution control is indicated as H, parameterized by the regularization parameter and S. Now, what is the importance is this connecting operator is in fact only dependent on the data. The Dirichlet to Neumann map, or Neumann to Dirichlet map, lambda over here, and the time reversal operator R, and the time integrator, the time filter. And in over here, a multiplier t minus t over here. And so we can solve this problem by only using the data and not knowing the wave speed. So we have sparsity, and so we insert the ISTA, the soft thresholding algorithm, and that is just written out here in its standard form. Here's the iteration to solve this sparsity regularized minimization problem. What we see here in red is where the data, the operator, appears. So it is interesting that it has an operator recurrent form. And well, here's the iteration to go from L to L plus 1. ISTA leads to the introduction of this function, sigma alpha, that in fact is the difference between two rectified linear units, namely the functions max 0, x minus alpha, minus the max of 0, minus x minus alpha. And as identified a long time ago, this leads to the natural introduction of an activation function, thinking of this as some form of a recurrent network. Of course, we need to discretize. We need to do the error estimates very carefully to build all these connections soon to be between some recurrent neural network and this methodology. All that was done in work by Korpela, Lassas, and Oksanen. And in fact, on the discrete level, we indeed can think of lambda as being an n by n matrix, in fact, bounded in operator matrix norm. And we can think of lambda actually lying in the closed unit ball of the n by n matrices, discretization up to level n. Indeed, what can be proven is that the ISTA algorithm in the limit of infinite iterations gives us the solution H alpha S, exponential convergence. And then the analysis of boundary control tells us, by taking the regularization parameter going to 0, that indeed we find the boundary control such that UH alpha S gives us the indicator function as wished. So now we are ready to introduce an architecture. And so I rewrote the recurrence ISTA that I wrote in a few slides ago. And so what we do is, well, we write it in a simple stacked form, in a generalized form, by stacking HL here, doing here the projection, and doing here the time reversal integration. So that is what I call HL. Then I can write it in a very simple form with matrices A theta, B theta, and here we see the introduction of what we call the bias vector B theta. There are terms that are subjected to sigma alpha, that's the nonlinear activation function, and there's a term that is not subjected to such an activation function, sort of a linear term. Now, boundary control tells us that if you look careful at these matrices, that the A's and the B's really can decompose into pieces that are very simple, like an identity matrix plus a second term. And these second terms have rank structures. In fact, they lie in Shelton classes. And that rank structure will lead us to sparsity, regularizing terms in the loss function that will greatly help us to get good regularization estimates and the like later on. Now, what we do is we need to repeat this for a whole sequence of values of S. And so we form a collection of these sort of networks and get the corresponding controls. Once we have these, we then take inner products with this function phi t, this multiplier function, take derivatives, and take the reciprocal. And that actually gives us then the wave speed at S equals Sj. So we collect these operations here in just some sort of function, at least continuous function G, where all these outcomes of these controls appear from this recurrent structure, and then it's sort of a post-processing we do to get the wave speed. And this indeed all can be made precise and exact. So let us now take the network point of view. A basic operator recurrent network, slightly more general than I wrote it before, not stacked, but in its basic form, that say has a depth uppercase L, is constructed by a recurrence relation, written here at the bottom, where the A's and the B's are matrices, and now we introduce weights or parameters that they depend on, theta and bias vectors L, and here I write the activation function that was sigma alpha before. And what we see here is this looks very much like a recurrent neural network, except that an operator or a matrix lambda appears here and here. And after you go to the second layer, this operation is nonlinear. These matrices do not commute. And so this changes, in fact, the structure of a recurrent neural network by having here a matrix input rather than, say, for example, a vector input. We can generalize that, as we encountered, by adding not just the previous layer, L minus 1 to L, but further down in the recurrence layers. And so we do that k times, and that just gives us the generalized form. Mind you that the width remains fixed, it's recurrent. So all these matrices A's and B's are n by n matrices, and all the bias vectors that appear here are n vectors. What I do here is I replace the activation function from a standard rectified linear unit to a leaky one, i.e. element-wise, standardly, we take the maximum of xj and eta times xj, where eta is some small parameter between 0 and 1. These networks can be related to one another by changing these activation functions, a detail that I will skip here. So a quick collection of all the information we have of this network that is born out of the boundary control method is, as I said, we can split, motivated by boundary control, all these matrices in components 0 and 1. 0 are very simple, basic, and so we won't learn them. The 1 components are in a Schatten class, and we factorize these matrices to express this explicitly and introduce vectors theta in the following way. Then we introduce the bias vectors, and so we collect all these things in a parameter set, and all these parameters we call lowercase theta. We collect them all, then is indicated over here. So we have parameters that form the weight matrices A and B, and then we have parameters that form the bias vectors. And we then distinguish index sets to these vectors, the index set that indices relate to the weight matrices P1 and to the bias vectors P2. P2, of course, is much, much smaller than P1. Now, when we write down such a recurrent network, we know a priori, well, from boundary control, what we are trying to accomplish, that the function we approximate is bounded by some norm, some L infinity norm. So we know that a priori, and so we can protect the network from not leaving these bounds by, in fact, adding 2 additional layers that cut off any element values that in some sense become too large. And that's what we do. So we apply this truncation using this prior bound, some prior bound of the function we aim to approximate. So here, essentially, we have generalized now the boundary control to this, what we coined the operator recurrent neural network. We had the linear operator, Neumann-to-Dirichlet map. The boundary control can be thought of as forming a holomorphic, using the holomorphic functional calculus, a holomorphic map applied to lambda and outputs another operator, q lambda. Then we subject that to a vector, and these form then the boundary controls that we're interested in. We have these indicator functions on the domain of influence, and then we substitute the outcome of that into this function g that takes inner products, differentiates, and so forth, and yields the reconstruction. So the general form consists of a holomorphic map acting on the operators and a smooth function g that's applied later. So let's make first a statement about the approximation of such type of functions of operators and the like by these operator recurrent neural networks. And so the point is we want to approximate accuracy epsilon. We control the domain on which the holomorphic function acts by a complex disk, radius 1 plus r, where r lies between 0 and 1, so the disk has a radius larger than that, centered at origin. G, let's assume that it is in CK. Q and G are both bounded, say by a constant 1. Then we can find a good approximation with a network not exceeding depth L0 and not exceeding width W0. Mind you that these are estimated in terms of the log, roughly speaking, of 1 over epsilon. So gives you an efficiency of approximation directly. It depends, of course, also on n, which is representative of the discretization that we have invoked in going from boundary control to the network. Then the point is, we have this function f that is composed of this holomorphic map and this function g, that gives f lambda, on the closed unit ball of n by n matrices in which lambda lives, and indeed with a network not exceeding these width and depth, we can approximate f by this network by accuracy epsilon. We can give estimates for expressivity of such a network. This network essentially can be thought of as generating local polynomial matrix polynomials, operator polynomials, and we can estimate the number of these regions of these local polynomial matrix polynomials. We can also estimate explicitly local Lipschitz constants, directional derivatives. That, of course, is important when one trains the network. At this point, I would like to now invoke the sparsity. I mentioned the Schatten class of boundary control, and we are going to exploit this as sparsity will play a big role in, for example, getting good generalization bounds. The sparsity is represented by essentially introducing the Schatten semi-norms of the weight matrices. So P1 was the index set of weight matrices. And this regularization term reflects this sum of semi-norms. We indicate it by R, again restricting the parameters theta to those of the weight matrices because we can't say much about the bias factors. Then we introduce the loss function in the standard way. Here's the standard loss function to approximate f by such an operator recurrent network. Introduce a regularization parameter, and here is the sparsity regularization term that we generate. Throughout, we will introduce a training set S of S samples, giving us the input-output pairs, say with a probability mu that we will encounter. That I will put a little bit under the table, and we can then introduce the empirical loss function by just looking at the error over just the samples in the training data, and again the regularization. Now let me highlight the sparsity. So let us look at functions that can be approximated with accuracy epsilon and with sparsity bound R0. So we refer to these functions as allowing such type of approximation if the regularization term with these parameters theta 0 indeed satisfies such a precise sparsity bound, and accuracy of approximation is epsilon 0. So these sort of give us a category of functions that satisfy, again, sparsity bounds and accuracy. And we introduce a bound for the loss L0 now, that if this definition applies, this sparsity definition applies, then L0 essentially can be expressed in epsilon 0 and R0, and if not, we stick to the L infinitum. And now the inequality constraint that the loss function, the empirical loss function, is less than L0, enforces that the regularization term is less than or equal than R0, which can be expressed in L0, where L0 again can be expressed in epsilon 0 and R0. With these sparsity bounds, we can do a variety of things. So we can look at the parameter set theta s, that is a local minimizer of the empirical loss function, and we can do sort of a counting argument of the number of parameters that appear through this regularization term. So let n be the number of indices of all these parameter vectors and dimensional vectors that are non-zero, the total, and let n1 be the number that are non-zero for the index set that relate to the weight matrices. Then we can give an estimate of these, namely as follows. This estimate of the number of indices, non-zero, vectors that generate the weight matrices can be expressed in terms of the sparsity bound and the regularization parameter. So what we see is that indeed by increasing the regularization parameter, the sparsity becomes directly reflected into this bound. So we can do an alternative constraint on, say, the feasible set of parameters theta by imposing this inequality constraint, where n1 is given by, well, the integer of this particular estimate. I should say I also introduced the notation n0, which is the total number, n theta of this, which is equal to n1, the number of indices non-zero vectors in the weight matrices, plus the ones of the bias vectors, which is 2 times the depth of the network for the linear and nonlinear terms in the recurrent relation. I would like to explore further the sparsity and the sparsity bounds. We can write the set of feasible parameters as the union, the finite union of compact subsets of linear subspaces of dimension of this n0 times n, and again, relates to discretization of boundary control, as follows, as this union, where m0 can again be bounded by, well, r0, the exponential here, n alpha. So again, we see that essentially the Hausdorff dimension of this set theta decreases when alpha, the regularization parameter, becomes large, when you enforce this sparsity. So let's now go further and cover the finite union theta just described. We can do with a finite set of balls of radius rho. So we're really going to describe it in terms of a finite set now with respect to the R norm. And we obtain the following result. Choose a rho greater than 0. Then there exists indeed a finite set containing these parameter vectors where the number in the set is bounded by R0 over rho to the power n0n, such that we can have a network, say, in the general parameter set here in the parameter set theta rho. And the difference between these networks is again expressed in terms of the exponent to R0, and here is the rho. So here you see as rho becomes small, how one converges to the other. And this is what we use in a moment in also our generalization bounds. These come over here. So the generalization tells us essentially when we have an empirical loss and we have an expected loss, how close these two are and how rapidly one converges to the other as we increase the training data. Of course, we would like that to be small. In fact, there's a parallel estimate of finding how well the optimal set of parameters performs compared to the exact result that I will not touch upon. I'll talk here just about this error gap. So let theta s again be the local minimizer of the empirical loss, subjected to this sparsity inequality bound as we have introduced. Consider the basic recurrent operator network. Then we can get a following estimate that the probability that this gap doesn't exceed delta, 2 delta, is 1 minus an exponential, which appears standardly in all these estimates that go back to the Hoeffding inequality, where this is a negative exponential in terms of S, in terms of the number of samples. However, there are these two constants, C1 and C2. C1 and C2 depend, of course, on this bound L0, but depend on the regularization parameter alpha 0. So what one would want to do to get a good result exploiting this sparsity is introduce a large regularization parameter. But we know from before that deteriorates the approximation. Mind you, you see also here the discretization n. So the better the discretization of boundary control, these constants grow with discretization as well. So this is true if L0 is bounded just by the L infinity norm of the function we try to approximate. That is now to the case that f can be approximated with accuracy epsilon 0 and sparsity bound R0 as we had introduced before over here. Then we improve the constants, in fact, by bringing the alpha and these exponentials down over here and here in C1 and C2. They now appear here as alpha in the power minus half over here and here. So the sensitivity to alpha is very different in this case using this sparsity if alpha is greater or equal than epsilon 0 squared R0. So exploiting sparsity, we get these very good generalization bounds. I should re-emphasize that it's important that there's an interplay between the regularization parameter, delta, the error gap, well, and of course the number of training samples, and these needs to be chosen judiciously to get an optimal result, to learn boundary control and learn the reconstruction of the wave speed. So this concludes the technical insight, how intertwined boundary control is in fact with deep learning through the introduction of an operator form of what we call operating recurrent networks. Let me just reflect on a few points. Of course, this is just one result. There are so many opportunities and challenges connecting imaging and inverse problems to deep learning. I mentioned that analysis leads to modified architectures that gives us great insights in greatly improved generalization bounds, understanding effective bias and the like. But many questions remain. Is it possible to get some sort of probabilistic anatomy of ill-postness of inverse problems? What about the training dynamics, subject of active research, and many other fundamental questions connecting the two? I did not touch upon anything related to like finite data and using priors, like deep priors. There's a vast literature on that that could connect to the ideas that I presented today. Jumping outside the imaging and inverse problem, there's a whole interesting world of starting just from the data, doing data-driven discovery, and we indeed have a program along these lines, and some of that is published in a paper with Berg and Johnson and Greg Barbosa last year in Science. Strategies for learning, natural framework for meta-learning, natural framework for transfer learning, and natural framework for reinforcement learning. I'd like to thank you for your attention. I will be very pleased to take questions.
So thank you, Maarten. I think that there were some glitches during the video, but overall it was okay. Thank you very much for this nice talk. Waiting for the audience to ask some questions, I could ask mine. At the beginning of the talk, you showed results both for sources and for reflectors. And the source problem, the inversion is linear, right? So the wave equation is linear in the source, while on the reflector, the source is nonlinear. Is there a difference in the architecture of the network that between the two that reflects going from linear to nonlinear? And Maarten, you are muted, so unmute yourself before trying to answer.
Yes, I should be unmuted now, I hope.
Yes.
Hopefully the internet works. Yeah, that's a very good question. And of course, there are many details under this presentation. Yes, you're right. There are two nonlinearities that you are very well aware of. That is the multiple scattering between the reflectors that is not accounted for in this network, that would require another recurrent structure. So that is not in the architecture that I showed. But there's also the nonlinearity in the background speed. Yes. And so the way we study that is by introducing a latent code, a sparse code for the background speed that I didn't talk about. And that becomes part of the parameters that go into the network. So we can actually use the reflection problem as a technique to do reflection tomography in principle for the background speed by trying to recover actually the code, say the sparse code of velocity models, assuming that a code or autoencoder is a reasonable thing to do for the background wave speed in the core scale. So that nonlinearity, we have a reasonable idea how to do that. The other one is possible, but proofs are still lacking that this will give indeed the right results. So the mathematics of it is lagging behind there. But yeah, very good and interesting points to be explored further.
Thank you. I have a question from the audience, so I will read it first. Wave-based imaging means which kind of wave? Nonlinear dispersive wave? Sorry, I missed your first part. Thanks. From Jiyun Chiao.
Yeah, so the wave equation that I considered in my talk was the scalar wave equation. And so think of it as the acoustic wave problem. So it did not account for dispersive waves in any way in the work that we did. It is a very interesting problem and could be subjected to similar techniques and approaches, but we have not done that yet. That is a very interesting.
Thank you, Matan. So waiting for other questions, I will ask another one. In the second part, there is the role of the regularization parameter alpha. It was very important. So I know there is a theory and we see the importance of the regularization parameter, but the question is, can we use this theory in order to get some recipe somehow of how to choose this regularization parameter in practice, or is there some insight?
Right, yeah, that's another very good question. Yeah, so we are doing numerics as we speak. And so, yeah, these very precise estimates of the constants, the C1 and C2, are very important to sort of come up with numerical choices of these parameters versus how large is the training data and so forth. So yeah, we use these quantitative estimates of the constants to follow numerical strategies for training such a network with a minimal number of training samples. But that is work in progress. We haven't done that. But yes, that is exactly the goal or the point of getting such precise expressions for the constants, not just the usual exponential estimates that you get. But yeah, we hope that will be very effective in following this training strategy.
Okay,
can I ask one quick question from a very applied perspective? So kind of building on what Crisula asks, are any of these theoretical results directly feeding into some of your current field work and experiments, the connections with deep learning?
Yes, that's a very good question. And so the answer is on the verge of being applied, yes. The FIO-net, we are linking into our work on earthquakes. And so in part in our program, we have been designing deep neural networks for unsupervised learning for detection of signals. We cross that, connect that to dense arrays, and then the FIO-net feeds in to localize these earthquakes. So at the moment, we are actually doing tests to do localizations of small earthquakes that are very hard to detect by standard techniques and finding where they actually originate. So yeah, we interface the FIO-net as we speak to our other work on this data-driven side. The recurrent network, the boundary control, is still far from a real connection to this type of application. But I hope we'll get to that.
Thank you.
So thank you very much, Maarten, and I would like to thank Stacy and Mickey for organizing all this SIAM meeting online. It has been challenging, and I hope that people enjoy it. So thank you all for attending. Thank you very much.
Thank you very much.
Thank you. Mickey, Stacy, Crisula, thank you very much. Stay safe.
Thank you all.
Bye.
Bye-bye.